everybody. Welcome to the chemistry lecture. It should be a fairly short one this time because this is part 2 from today, November. What is today? November 25th, if I'm remembering. No, we are far past the 25th. November 29th, which means I may need to go and change the title of my last one. Once again, something went wrong. We recorded the first half of the lecture. Second half of the lecture is gone. So this is going to be fairly short. We're going to continue the discussion from the first half. This is part 2. We've been talking about nuclear chemistry and all of that kind of fun stuff. When we laugh on. Let me start this back up. This will be fairly short. When we left off, we had finished going through the decay rate, the decay of radioactive decay of naturally occurring uranium in the soil. We ended up down to mercury, the heavy metal poison mercury. And we saw how radon kind of gets into the house, and that is one of the products of the uranium decay. All right. Well, unfortunately, once again, I am not going to erase what I did on my tablet because that's how I know what to cover and in what order. I want this to be as close to the original lecture as I can get it. So I make sure that I cover all of the same things that I covered there. This kind of, the fact that I've already drawn this out is kind of a reveal that I did not have the first time. But we started talking about half-lives. There's a movie, and I wish I could remember which one it is. Anyway, I want to say that it's Canadian Bacon with John Candy. Very, very funny movie. If I have the wrong movie, it's still a movie worth watching. And in the movie, they make a reference that actually is true. Even though the movie itself is a comedy, this is actually true. There was a small breakaway republic called Kazakhstan that you very well may never have heard of. And this little republic was, for a time, one of the world's major nuclear superpowers. Here's how that went about. After the Berlin Wall fell, circa 1990-ish, the Soviet Union eventually fell apart some years later. 95-ish, maybe, somewhere around there. And when it fell apart, the Soviet Union fell apart, which is now why we no longer refer to the Soviet Union. We talk about Russia. When it fell apart, all of these little nations started cropping up. And I really honestly wish that one of them had been called Kuchi Kuchi, because then if there was ever a revolution, it would have been the Kuchi Kuchi coup. One of these breakaway republics was called Kazakhstan. And when they gained their independence, when Russia pulled out from that region, they left behind their nuclear arsenal that was in that area. So for some time, Kazakhstan was one of the major nuclear powers in the world. Is it something we need to worry about? Well, no, for a few reasons. First of all, Russia never gave Kazakhstan the launch codes, so they couldn't really use the nuclear weapons anyway. Secondly, eventually Kazakhstan called on the international community to help them disassemble the nuclear weapons. So honestly, they don't even have them anymore. They also had, by the way, chemical weapons and biological weapons, and those were destroyed as well. But the other reason, the other reason that we don't have to worry about it is because in order for a bomb to go off, the uranium or plutonium, depending on what the fuel core is made out of, must be excessively pure. Excessively pure. I have been threatening for some time to tell you how to make an atomic bomb. I'm going to, a week from today. It's actually a very trivial thing to do. You can make it with Legos. But the reality is, the real problem is getting the pure fuel, uranium or plutonium, that's pure enough that it will actually go off. That's where the problem comes in. Back when I was teaching in South Dakota, down in the basement, we had uranium ore. Uranium ore is just dirt. It just happens to have uranium in it. As a chemist, if I wanted to, as a chemist, I could have purified the uranium out of that ore. It's a very simple thing to do. React it with a little bit of acid, dissolve it into a solvent, and then crystallize it back out again. And lo and behold, you have uranium. But the uranium that I would have had would have been a mixture of naturally occurring isotopes with an average atomic mass of 238, whatever's in the periodic table. That will not explode. As a chemist, yeah, I can do that. That's trivial. The reality is they need a very specific isotope of uranium in order to get it to give off an atomic bomb. That is far more difficult because the problem is every isotope of uranium reacts chemically like every other isotope. So chemically, I cannot isolate a single isotope out of that collection of uranium, which is why, even if I did it, well, I would have created a mass that was too radioactive, which is not good, but that's why it never would have been a problem if I had purified the uranium, which of course I don't want to do anyway. Who would want that crap? In order to purify specific isotopes requires very highly sophisticated physics equipment, requires centrifuges, massive centrifuges. And not just simple centrifuges. They don't just spin around and around. There's actually more engineering to them than that. So it's not just centrifuges, but in order to purify uranium, it takes the kind of resources that as a person I wouldn't have. You actually need the resources of a government to be able to purify and enrich a specific isotope. But the thing is, even once you purify this isotope, and it has to be 99.99 some odd percent pure, it has to be more pure than ivory soap. It has to be really pure, or it's not going to detonate. And we'll talk about why a little bit later, probably on Thursday. But it has to be excessive. And you can't keep it pure because it doesn't matter what it's contained in. The radioisotopes decay naturally on their own. Given time, the uranium, the purified uranium itself, will produce the lead, the mercury, the contaminants that will deactivate the uranium core so that it is no longer capable of undergoing an explosive reaction. It's been said, and I don't have the numbers to, actually, I probably do in one of my books back here, but they have to replace those uranium cores in any atomic or nuclear weapon every 5 to 10 years. The government won't say exactly how often they replace them, but after, I think if I'm remembering correctly, after 10 years, there's only a 50% probability that you'll actually get an atomic reaction if you try to detonate one of those bombs. So if the average age of those weapons in Kazakhstan was 5 years, that means 5 years later, the entire arsenal, there's only a 50% chance that any given bomb would go off. Now, 25 years later, they would be too impure. You would never be able. You make a dirty bomb. I mean, you blow them up, you'll get radioactive waste thrown over however far the explosive is that you're using, but it won't be an atomic bomb. One of the things that people often misunderstand is the concept of half-life. This is one of the things I talked about before, so I'm going to talk about it now. First of all, people kind of misunderstand half-life. If you have a half-life of, say, 100 years, for example, a lot of times people think, oh, well, then after 100 years, the area must be safe. Well, no, that's not what it means. In fact, the definition of half-life, what half-life really means, is that it's snowing here. I was just taking a note because I was thinking about making a run, but maybe I'll wait till tomorrow. What half-life really means is that after one half-life, if the half-life is 100 years, after 100 years, you will have half of the original concentration of whatever it is that you're talking about. So it's not that the area is safe. It's just that half the potency is gone, and half that potency can still be toxic. So it's not just a question of waiting one half-life. It's a question of how many half-lives you have to wait until it finally does become safe. The other thing that a lot of people don't understand about half-life is the way the decay works. So here we are with my chart that I've drawn up. So in one half-life, suppose we are good enough, and we're not. Suppose we are so good that we can come up with 100% pure. This is percent here. 100% pure weapons grade uranium or plutonium or whatever it is that you happen to be making. That means that with the definition of half-life, after one half-life, like I say, it might be 100 years, it might be 50 years, I don't know, that you're down to a 50% concentration. Now, a lot of people think that if you're at 50% concentration after one half-life, then surely after two half-lives, you would be at zero. No, that's wrong. Because for the second half-life, you are starting with a concentration of 50%, which means that my cat was very upset with this conversation, which means that after two half-lives, we go down half of the 50% concentration. So after two half-lives, pardon my voice, puberty, you know, after two half-lives, boy, I just chirped at the same place. After two half-lives, we are down at 25% concentration. So are we done to three half-lives? No, we're not, because after three half-lives, we're down from 25 to 12.5%. This concentration keeps getting closer and closer and closer. My cat keeps getting closer and closer and closer to zero, but it never quite reaches zero. Now, mathematically, it will never reach zero. In reality, there's a finite number of uranium atoms, We can figure out exactly how many that is based on Avogadro's number. But even at that, there are so many of them that it looks like infinity to us. So it may as well be an infinite number. So yes, this will never, ever reach zero. We say that it becomes asymptotic to zero, which means it just keeps getting closer and closer and closer to zero, but it never quite reaches. There's actually a very elegant little equation that you can use to figure out just how long it will take to reach a given specific calculation that you want, which we're not going to go into because that's kind of beyond the scope of this course. We're going to stop sharing here. But again, I knew that this would be a short segment because we ran really long in the first half talking about the decay rates of uranium. So this pretty much wraps up this half of the reaction. Now we have more to talk about in nuclear chemistry Thursday, and we will wrap that up. Once again, what I'm going to do for special topics, so a week from today, I'm going to teach you what it takes to make an atomic bomb. In fact, I feel like I should make some notes here because what I want to talk about Thursday, I want to talk about chain reactions. And certainly we're going to talk about critical mass. And we probably will talk about nuclear power, clean nuclear power, civilian nuclear power, and how that works as well, which is kind of fascinating. That's going to get into the realm of physics and how we generate electricity, because what we are doing with nuclear power is just remarkably simple. You're going to just be astounded at what a silly little thing nuclear power is really doing to generate electricity. So I'm looking forward to that. That'll be Thursday. Next week, a week from today, amuse your friends, annoy your enemies, build your very own fission, fusion, fission atomic warhead at home. You can build your own. Actually, it's kind of simple. Well, no, it's easy to make an atomic bomb. Making a nuclear bomb is a little more complicated. And then, like I say, a week from Thursday, I'm going to reveal something I've been bragging about on Facebook, a breakthrough in hydrogen bonding in my research. Now, it has been verified, so I can't say that we're going to talk about what the hydrogen bond is, but we're going to talk about my hypothesis and my breakthrough. That I think is unique. I think it's new. So it should be fun. If you watch that one, you may know more about the hydrogen bond than literally anybody else in the world, including your chemistry professor, unless I'm your chemistry professor. But it should be a lot of fun. So I will see you then. Thank you for watching part 2.